In the last video, we were introduced to standing waves and some of the terminology involved. In this video, which is the last one on waves, we'll discuss standing waves on a string in more detail, and we'll also discuss standing waves in an air column. For standing waves on a string, the ends of the string are fixed in place, so the ends of the string must be nodes. And so this is what the fundamental frequency looks like, which is also referred to as the first harmonic frequency. Now let's develop equations for the fundamental frequency and for its wavelength in terms of the length of the string L. Starting with the wavelength, we just need to recognize from the diagram here that there is a half of a wavelength in the length L. And so solving that equation for the wavelength, we find that the equation for the wavelength of the fundamental is 2 times L, and we'll give it a 1 subscript because it's the first harmonic. Now to find an equation for the frequency, we'll start with the common wave relationship, speed equals frequency times wavelength, and then solve that equation for frequency, and substitute the equation we just found for wavelength into this equation, which gives us the equation for the fundamental frequency. Again, we give it a 1 subscript because this is the first harmonic. As you can see, the frequency of the fundamental standing wave depends on the length of the string and on the speed of the wave in the string. Since this is a standing wave, it might seem odd to discuss the speed of a wave on a string, but recall from the last video that standing waves are actually the superposition of 2 waves traveling in opposite directions. And so we can write down the speed of a wave on a string. You may recall that the speed of a wave depends on the medium and, more specifically, the elastic and inertial properties of the medium. The equation for the speed of a wave on a string is this, where T is the tension in the string and the Greek mu is the length density of the string, or in other words, its mass per length. So T is the elastic property of the string, which is also the restoring force, and mu is the inertial property of the string, which, as we just said, is a length density. Now let's look at the next resonant frequency. In general, each subsequent resonant frequency can be found by adding another node into the standing waveform. So if we add another node to the fundamental frequency, the next resonant frequency looks like this, which is referred to as the first overtone from the fundamental frequency. We can derive equations for the frequency and the wavelength of the first overtone, just as we did with the fundamental. Starting with the wavelength, we can see that this time there is a complete wavelength in the length of the string L. So the wavelength of the first overtone is just L. We can derive the equation for the frequency of the first overtone just as we did with the fundamental frequency, starting with the relationship speed equals frequency times wavelength and solving that for frequency, and substituting for the wavelength, the frequency of the first overtone is V over L. Recall that the fundamental frequency was V over 2L, so the frequency of the first overtone is just twice the fundamental frequency. Because of this relationship, we call this frequency the second harmonic, and so we give the frequency a 2 subscript. Similarly, the wavelength is 1/2 the fundamental wavelength, and we likewise give it a 2 subscript. Now let's look at one more resonant frequency. We get the next resonant frequency, which is the second overtone, by adding another node into the waveform. We can derive the equation for the frequency and the wavelength just as we did before. This time there are 1.5 wavelengths in the length L, which I'll write as 3 over 2, so the wavelength is 2/3 L, and that is 1/3 times the fundamental wavelength. And deriving the frequency the same way as we did before, we find that the frequency is 3 times the fundamental wavelength. And so this is referred to as the third harmonic. And so I've given the wavelength and the frequency subscripts of 3. At this point, I think it's nice to see a summary of the equations we've just discussed because it makes it easy to see the pattern of the harmonic equations. We have the wave speed equation and the equations for the wavelength and the frequency of the fundamental. The subsequent harmonics are just multiples of the fundamental. The second harmonic frequency is 2 times the fundamental, the third harmonic frequency is 3 times the fundamental, and then the fourth is 4 times, and the fifth is 5 times, and so on. Similarly, the wavelength of the second harmonic is 1/2 times the fundamental wavelength, and then the third and the fourth and the fifth, and so on. Now let's look at the standing wave in an air column. When you blow across the top of a soda bottle and produce a tone, you're creating a standing sound wave inside the bottle. This is the basis of musical wind instruments. We'll consider 2 basic constructions. One when the container is a tube that is closed on one end and open on the other, which is basically the situation with the soda bottle, and another when the tube is open on both ends. Let's start with a tube that's open on both ends. We can analyze standing sound waves in much the same way we analyze standing waves on a string. But first, let's visualize what's happening when a standing wave is formed in an air column. Here's a simulation of the fundamental standing wave in a tube that's open on both ends. The dots represent the movement of air molecules. As you can see, the air molecules oscillate in and out of the ends of the tube, but they don't move at the center of the tube. Just like with the string, the location where the molecules don't move is a node, and the location where they move the most is an antinode. It's convenient to represent the motion of the molecules with the same diagram that we used with the string, like this, where you can see the node in the middle and the antinodes on the ends. We get the first overtone by adding another node inside the tube, like this, where now you can see that there are two nodes inside the tube. And we get the second overtone by adding another node like this. So now there are three nodes inside the tube. With this plot, we can derive the equations for the frequency and the wavelength, just as we did before. Let's start with the fundamental, that's also the first harmonic. The length is equal to a half of a wavelength, so the wavelength of the first harmonic is equal to 2L. For the frequency, we can again start with the relationship V equals frequency times wavelength, and solve that for the frequency and substitute in the wavelength, and we find that the frequency of the first harmonic is V over 2L. Again, we find that the frequency depends on the wave speed in the medium, which is the speed of sound in air in this case. The speed of sound in a fluid, such as air, can be calculated with this equation, where beta is the bulk modulus of the air and is the elastic property of the air, and the Greek letter rho is the volume density of the air and is the inertial property of the medium. Now let's derive the equations for wavelength and frequency of the first overtone. L this time is a full wavelength, so the wavelength is equal to L, which is half of the fundamental wavelength. And then the frequency, derived in the usual way, is V over L, which is twice the fundamental frequency. So we refer to this as the second harmonic. And then for the second overtone, the wavelength is 2/3 L, or 1/3 of the fundamental wavelength. And the frequency is 3V over 2L, or 3 times the fundamental. So we refer to this resonant frequency as the third harmonic. As we did for the standing waves on a string, we can summarize the equations in terms for the standing waves in a tube that's open on both ends. We have the wave speed equation, which is the speed of sound in air, and then the equations for the first three harmonics. As you can see, these harmonic equations are the same as the ones for the string. And so we have the same pattern that we did with the string, so the frequency of the fourth harmonic is 4 times the fundamental frequency, etc. So now let's go through the same analysis for the standing waves in a tube that is closed on one end and open on the other end, like a soda bottle. Let's start with the simulation to visualize what's happening. Here's the fundamental. This time there's a node on the closed end of the tube and an antinode on the open end of the tube. And then we get the first overtone by adding a node inside the tube like this. And then we get the second overtone by adding another node inside the tube like this. Now let's derive the equations for the wavelength and the frequency of each standing wave. The procedure will be the same as before, but we'll wind up with a different pattern for the harmonics than we did with the other standing waves we analyzed. As usual, let's start with the fundamental or first harmonic. This time there is 1/4 of a wavelength in the length of the tube, so the fundamental wavelength is 4L, and the fundamental frequency comes out to be V over 4L. Now let's look at the first overtone. There are 3/4 of a wavelength in the length of the tube, so a wavelength is 4/3 L, and that is 1/3 of the fundamental wavelength. And the frequency comes out to be 3V over 4L, which is 3 times the fundamental frequency. So now the first overtone is actually the third harmonic. And so the second harmonic frequency, which is 2 times the fundamental frequency, doesn't produce a standing wave and is therefore not one of the resonant frequencies. And so let's look at the second overtone. Here there are 5/4 of a wavelength in the length of the tube, so a wavelength is equal to 4/5 L, and that is 1/5 of the fundamental wavelength. And the frequency comes out to be 5V over 4L, and that's 5 times the fundamental frequency. So the second overtone is actually the fifth harmonic. And so this pattern continues so that the third overtone is the seventh harmonic, and the next overtone is the ninth harmonic, and so on. What we find then is that for a tube that's closed on one end and open on the other end, only the odd harmonics produce standing waves and are therefore resonant frequencies. And so here's a summary of the standing waves for a tube that's closed on one end. The equation for the speed of sound is the same equation we use for the tube that's open on both ends, because we're still talking about the speed of sound in air. And from the pattern, we can see that only the odd multiples, and therefore the odd harmonics, produce resonant frequencies in this case. And so that brings us to the end of this video on standing waves and on the topic of waves in general.